Let's begin our study of thermodynamics. When I was in undergrad as a physics major, I had to take a whole semester-long course about thermodynamics. When I was in grad school, I had to take another semester-long course about thermodynamics. So it's a very important topic in physics, and we're just going to get a little sliver of it in our class here. So there are two laws of thermodynamics. Here is the first one. The first law of thermodynamics is that the change in internal energy of a system equals the net heat transfer into the system minus the net work done by the system. Okay, so the first law of thermodynamics is just an equation. Here is the first law of thermodynamics in equation form. U here is the internal energy of a system. This quantity that we're calling U is the sum of all the kinetic and potential energies of all the atoms and molecules inside a system. So remember, to make a system, you have some experiment or you have some area of space and you just draw a circle around it. That's your system. You can quantify your system however you like. We're just going to draw a bubble around our system. And everything inside there is what constitutes our system. The change in internal energy of our system is this delta U here. Okay, Q is the net heat transferred into the system. It's the sum of all the heat transfer into and out of the system. So really Q is a net heat transfer. So Q, the total value for Q is equal to the heat transfer into the system minus the heat transfer out of the system. Okay, that's what Q represents here. So Q is actually equal to the heat transfer in minus the heat transfer out of our system. And then the work is the total work. It's the net work done by the system. And so W is the sum of all the work done on or by the system. So W is equal to W out minus W in. All right, so that's our first law of thermodynamics. So we're going to use it as an application a little bit later so you can see how it works in practice. Okay, now there are some kind of confusing sign conventions when we're working with the first law of thermodynamics, and it differs depending on which textbook you use. Then that's kind of confusing too. But here, we're going to use the following sign conventions. Our value here for Q is positive if there is a net heat transfer into the system. So Q in is greater than Q out. Okay. W is positive if there is net work done by the system. Okay. So if W out minus W in is positive, that means that the work output of the system is greater than the work put into the system. If that quantity is positive, we say that the system does work. There's work done by the system. Okay. If the work into the system is greater than the work out of the system, then W is going to be negative here. And so that means that work is done on the system rather than work being done by the system. Okay, so a positive value for Q here adds energy into the system, and positive W takes energy away from the system. And the internal energy U of our system is the sum again of all the kinetic and potential energies of all the atoms and molecules wiggling around inside that system. Now we're going to apply the first law of thermodynamics into a problem so you can see it in action. Suppose there is a heat transfer of 40 joules into the system, so that will be Qn, while the system does 10 joules of work. If the system does work on its surroundings, that's a work that we call out. That's a work out of the system. It's doing work on its surroundings. That's an output work that the system does. Okay. Then later, there is a heat transfer of 25 joules out of the system. So Q out will be 25 joules, while 4 joules of work is done on the system. If work is done on the system, then we call that a work that's done into the system. So we'll call that WN. That's work input into the system. What is the net change in internal energy of our system? So delta U is equal to Q minus W. So then the net change in internal energy of our system is going to equal, we earlier said that Q here, the net heat transferred into the system, is Qn minus Q out. So we had 40 joules in, we had 25 joules out. 40 minus 25 is 15. So Q, net heat transferred into the system, is 15. Now, we've got to have Q minus W. W, we quantified earlier. W is the net work done by the system. That work done by the system is going to be the work that the system does, the output work, minus the work done on the system, which is the input work. Okay, so this W here is the output work minus the input work. So our system here did 10 joules of work on its surroundings, but also 4 joules of work was done on the system. That was an input work. So this work here, this W, is going to be the work out minus the work in. So it'll be 10 joules minus 4 joules, so that's 6 joules. We've got 6 joules out of the system. So 15 joules, which is our heat transferred into the system, minus 6 joules, which was the work done by the system, is equal to 9 joules. That's the change in the internal energy of our system. We can apply the first law of thermodynamics to some simple processes. And in this case, we're going to think about a gas, and we're going to think about our first law of thermodynamics within the gas. And there are 4 different types of processes that we're going to talk about here. The first one is called an isobaric process. Isobaric means constant pressure. In an isobaric process, a gas does work on a piston at constant pressure. Okay, so here we have a cylinder filled with a gas, and we've got this piston on top of that. Okay, and so the gas inside this cylinder is going to do work on the piston. The only way that this gas can do work on the piston is if this gas changes volume. Okay, so we are going to use this expression that work is equal to the pressure times the change in volume of the gas. Pressure is going to be constant here in the isobaric process. So the only way we can do work on this piston is if we change volume. How do we get that this work is equal to pressure times the change in volume? Well, the work is equal to a force through a distance. We've already seen that. Remember that also we can say that pressure is equal to force over area. We talked about that when we were working on fluids. So if you solve that equation for force, force is equal to the pressure times area. So you can replace the force here with pressure times area and then times D. If you have an area, like a cross-sectional area, and you're multiplying it by a distance, that's a volume. And so you have that the work is then equal to the pressure times the change in volume. Now our gas can only do work then in an isobaric process where pressure is constant if we change the volume. And this can only happen, this change in volume at constant pressure can only happen if we have some net heat that's being transferred into the system. Now this is also a really great place to talk about how the work performed by or on a gas is equal to the area under the curve of a P versus V diagram. So here we have a diagram where we've got the pressure of the gas on the vertical axis, we've got the volume of the gas on the horizontal axis. In an isobaric process, let's say we move from point A to point B in an isobaric process. Isobaric means constant pressure. We keep the pressure constant, but we're changing our volume. And the area underneath this P versus V diagram, or this purple shaded area here, is going to be the pressure times the change in volume. So that's this area here, and that's also equal to the work. So the work done by gas is equal to the area underneath the P versus V diagram. An isochoric process is sometimes called an IsoVolumetric process. That's a process where the volume of the gas doesn't change. We saw earlier that the work that is done on or by the gas is equal to the pressure times the change in volume. If we have no change in volume, then we have no work that can be done. Okay, so if you plot an isochoric process on a P versus V diagram, the isochoric process, isovolumetric process, forms a vertical line. Okay, so if we come over here and look at, let's say that we have a thermodynamic process happening in a gas, and it goes from state A to state B in this first leg of its cyclic process. Along points A and B in our P versus V diagram, we have an isobaric process. We have a constant pressure. But now between points B and C, we're going to have an isovolumetric process if we go from P to V. And there's no area that you can have underneath the curve if the curve is a vertical line from B to C. So our gas does no work, even if we're looking at a P versus V diagram, because there's no area underneath this vertical line here. So this is a good point, since I have these P versus V diagrams here, to talk about the cyclic processes and the work that's done by a cyclic process if we can graph them here on the P versus V diagram. So for example, we have a cyclic process that goes from A to B, isobaric, then B to C, isochoric, then C to D, isobaric again, and then D to A, isochoric. So during this entire cycle, the work that is done is the area enclosed within this cycle. So the work done is the area within this cyclic loop. And the final two processes are called isothermal, so constant temperature, and adiabatic. In an adiabatic process, there is no heat exchange. So the heat of the system remains constant. The heat into the system is the same as the heat out of the system. Okay, so isothermal processes occur at constant temperature. So here we have an example of an isothermal process. We go from A to B, we change pressure, we can change volume in an isothermal process, but all along this line here that we call the isotherm, the temperature remains constant, but we can still change our pressure and volume. In an adiabatic process, you can have a change in temperature, but there's no heat exchange between outside and inside the system. When you have an adiabatic process where there's no heat exchange, so Q remains constant, then you can change temperature by changing the pressure and volume of the system, but again, there's no heat exchange. So here's an example of an adiabatic process. From A to B up here, it was an isothermal process. We changed pressure and volume, temperature remained constant. Here we have an adiabatic process where we go from A to B. The temperature will change in this case. We will change pressure and volume, but there's no difference between the heat into the system and the heat out of the system. All right, so now let's synthesize those ideas that we just talked about with the 4 different types of thermodynamic processes. So here I have a P versus V diagram. And along these blue lines here are what we call isotherms. Those are regions in the P versus V diagram where you can change pressure and volume, but the temperature remains constant. So anywhere along one of these blue lines, temperature remains constant. And so we have 4 paths here. They're all starting from the same spot. We've got paths A, B, C, and D, and you're going to identify them according to their trajectory here on the P versus V diagram. Those 4 different thermodynamic processes according to their graph here on the P versus V diagram. So we have isobaric, where we have constant pressure. If we have constant pressure, our gas can do work by changing volume. So work is equal to P delta V. Isochoric processes, that means constant volume. If you don't have any change in volume, then your gas cannot do work. Isothermal processes, those are processes that happen at constant temperature. So if there's a constant temperature, we have no change in the internal energy of the system. Temperature is a reflection of the internal energy of the system. So if you don't change temperature, you don't change the internal energy of the system. Remember that our equation for the first law of thermodynamics was delta U is equal to Q minus W. So if delta U is equal to 0, then that means that Q has to equal W. So in an isothermal process, you have the net heat transferred into the system must equal the net work done by the system. And then in an adiabatic process, we have no heat transfer. So that means that Q is equal to 0 in that case. So for our first law of thermodynamic, we have delta U is equal to Q minus W. So if Q is 0, then that means that our change in internal energy has to equal minus W. But in any case, that's just a summary of those 4 different types of thermodynamic processes. And I want you to match up these different types of thermodynamic processes with the paths here, A, B, C, or D. And that's going to be the question that you answer for this engagement check.